Okay, let's go ahead and start. I'm pleased to be able to introduce Pierre Baldi. So he is Chancellor's Professor of Computer Science at UC Irvine. He's done a lot of work in machine learning and in the interface between machine learning and the life science, bioinformatics, chemoinformatics. He's won a number of awards, and he's also a fellow of the ACM, AAAI, and IEEE. So, thank you.
Thank you. Can you hear me in the back? So it's a pleasure to be here. Thank you for the invitation. And this is the roadmap for this presentation. I'm going to tell you very briefly what the basic problem is, and then go a little bit into an overview of the history of the problem. I don't plan to be exhaustive, I don't claim to be exhaustive, but I'll try to connect a few important dots, starting from the 1950s up to today, and then most of the time I'll spend on the algorithms and a little bit of theory about these deep architectures and deep learning, and show you one example of application towards the end. So as far as we can tell, learning is essential for building intelligent systems. Whether it's carbon-based systems or silicon-based systems, they all use learning to try to do difficult tasks. And when trying to do a difficult task, this system never do them in a single step. It always requires a number of steps. And so the idea is that you have a system with many steps. You have learnable functions that have parameters between the different layers, and you want to learn a certain input-output function from examples that are given to you. And that's a deep learning problem. How do you adjust the parameters of all the functions that are between the layers, especially layers that are deep in the architectures, in the architectures that do not see exactly what goes on in the outside world, that do not have access to the input or the output targets. So in very vague terms, that's the kind of problem that we're going to look at. And a question that comes up all the time is, how deep has the network to be in order to be deep learning? Well, there is not a precise answer to that. The short answer is more than one layer. If you think about vision in the human visual system, we can recognize the images in about 200 milliseconds, and it takes about 5 milliseconds to traverse a synaptic cleft. So even in rapid visual recognition, we're not dealing with millions of layers, something like 10, 20, a small number. So that's the kind of things I have in mind when I mention deep architectures and deep learning. So a little bit of the history of this, starting in the 1950s, and I'm sorry if you just had lunch. This is really the foundation, the starting point, I think, for all the ideas in machine learning and in AI, is the study of the human brain. So around 1950, a lot of the concepts we have today were already in place. People knew that brains had specialized area, Broca, Wernicke, for instance, areas in speech. If you have lesions here, you get all kinds of speech deficit. Of course, people knew from Darwin that the brain has been built by evolution. They knew about synapses. This is Sherrington, who coined the word synapse. Ramon and Cajal had done beautiful studies, staining studies of cells, so they knew about Purkinje cells in the cerebellum, pyramidal cell in cortex, 6-layer architecture of the cortex. A lot of these fundamental anatomical ideas were in place. And of course, Hodgkin and Astley had studied action potentials, how neurons communicate with each other, had built their famous model. And on the theoretical side, I just put here Shannon, of course, had developed information theory a few years before. This is von Neumann, who had built the first computer. By the way, von Neumann wrote a little book about the brain around that time. It's a very interesting book to read if you find it. And McCulloch and Pitts had already introduced the idea of artificial neurons, those very simple neurons that take a weighted linear sum of their inputs and then use a threshold or a sigmoidal function to produce an output. So all these ideas were already in place. And so you could start asking the question in 1950, where does the brain stores bit, right? Where are your memories? Where do you store your telephone numbers? How do you learn how to play an instrument, etc., etc.? And you can do a back-of-the-envelope calculation that you cannot store bits in electrical signals. It would be way too expensive. You would lose a lot of weight very rapidly. So bits have to be stored ultimately biochemically in the brain. And the natural place to think about storing this information is in the synapses, which are the points of contact between the neurons. So already at that time, people had made the hypothesis that learning or information storage is implemented by modifying these synapses in some complex ways that we still don't understand very well today. So that's a very nice model, but if you start thinking about it, you should see that it's in fact raises a very difficult and profound question, which is the following. To see it, you have to rescale things, and imagine you rescale everything by a factor of 1,000,000. Then a synapse, imagine that you're trying to learn how to play tennis or play the violin. A synapse is the size of my fist. And then the diameter of a neuron is about 10 meters. So this room is the neuron. And then the tennis racket is in New York, or maybe even in Florida, something like that. So how is it possible that this little synapse, which is completely blind, only recognizes its immediate, physical-chemical environment? How can it adjust itself so that you improve your ability to play tennis? How does it know what to do, right? That's very mysterious, and that's a fundamental problem of learning, and it's a deep learning problem because you have these many layers. If a synapse is on the periphery, either on the visual perception, let's say, or maybe on the motor side, you can have some idea of what the synapse is, how it could get a signal for what to do. But if the synapse is deep in the brain, 10 layers away from the periphery, how does it decide what to do? So the first person that wrote about this fundamental problem and came up with some ideas is, of course, Hebb, who was a psychologist and wrote a book, The Organization of Behavior, in 1949. And it is in this book where he has this famous sentence, which is sometimes summarized by neurons that wire together, fire together. This idea that there is correlation in the firing, and that is what is used by the synapses somehow to adjust themselves. This is a very simple form of what today would be called the Hebbian learning rule. There is many other forms, and by the way, nowhere in the book would you find any mathematical equation or anything like that. But it's the first time that at least some idea of how this very mysterious problem of how deep synapses could adjust themselves, this is a possible idea of how this could be happening, that synapses are looking at correlations between pre- and postsynaptic neurons. Now, this doesn't explain how you get organized behavior on a larger scale, but at least it gives some idea of how a synapse could decide whether to strengthen itself or weaken itself. A few years later, Rosenblatt introduced the perceptron learning algorithm. So again, here is this very simple neuron models with a threshold gate. And he found a very simple, if you have input-output training data, for instance, classification of a bit string or some kind of image, there is an algorithm, and if things are linearly separable, the algorithm works very well. So that was Rosenblatt's contribution. And Widrow made it a little bit more general by using, instead of having a threshold gate, by putting a sigmoidal function here. And they found a more general learning rule, which is nothing else than gradient descent, which generalized the perceptron learning rule. Which all these rules, they sort of look Hebbian, because to modify the weights between neuron or perceptron I and J, you basically need the presynaptic intensity, and you multiply by a postsynaptic term, which is the error, the difference between the target, what you should have gotten, and your actual output. So all that is nice until Minsky and Papert came along They wrote this book, Perceptron, in '69, proving a lot of interesting theorems about Rosenblatt perceptron learning theorem, showing that even if data is not linearly separable, you get something that behaves reasonably well, for instance. But they wrote this sentence. I don't know why the image is truncated here. But the sentence says that there is no reason to suppose that any of these virtues, the virtues of the single layer perceptron, carry over to the many-layered version. So they were unable to see how a multi-layer perceptron can learn anything. And of course, they were edging their bet. If you look at the following sentence, nevertheless, we consider it to be an important research problem to elucidate or reject our intuitive judgment that the extension to multi-layer system is derived. But anyway, this is the sentence for which they received a lot of flack. People claim that they sort of paralyzed AI and machine learning developments in the 70s. I don't know if it's really that bad, but the fact is that the problem came back in the 80s, so that's really when machine learning started. And there were different groups in different places, not talking very much to each other that started the process. I think at the time, the most influential one was the group by John Hopfield at Caltech. Hopfield actually got his PhD here at Cornell, so he's a Cornell graduate. But Hopfield developed a model where he took perceptron, connected them with symmetric connections, and applied Hebb rule. That's basically what the Hopfield model is. And it has interesting properties, it is conversion, etc. And that created a lot of excitement, brought many physicists into the field, and that's when NIPS and Snowbird Conference were started, etc. Judah Pearl was starting to work on graphical models, and although he was not very known in the machine learning community at the time, and Les Valiant had written his paper on the theory of the learnable. By the way, this two got the Nobel Prize in Computer Science over the last 3 years, the Turing Award. So that shows that machine learning has come a long way over the last 30 years. But in the 80s, the word machine learning actually didn't really exist. But the group that had the greatest practical influence and that took on the Minsky-Papert challenge is the PDP group at UCSD that was led by David Rumelart and other people that participate in that group that you probably recognize, Jeff Hinton, Francis Crick, and Terry Sinofsky. That's the group that introduced backpropagation, which is nothing else than gradient descent in a multi-layer neural network. So it's the chain rule. If you apply the chain rule, you get backpropagation, something that Newton could have done easily if he had known about neural networks. But it was done in 1985. And when you look at the rule, at the end of the day, if you take, again, a deep weight in the architecture, and you want to change this weight, you get a learning term that is the product of two terms, a presynaptic term, which is the output of this neuron, and a postsynaptic term, which is the backpropagated error that comes from the output layer. And that's a term that is not local, not Hebbian, and is problematic, because you compute your error at the output layer and then you propagate it backwards. Every time you have to multiply the error terms by the transpose of the forward weights, that's fine. And then you have to multiply by the derivative of the logistic or whatever other nonlinear functions you're using in each layer. And if you're using logistic functions, after a little bit, after some learning, you are in the flat part of the logistic functions. Your derivatives are close to zero. Every time you traverse a layer, you multiply by zero, essentially. Very rapidly, you run into machine precision problems, and that's why learning cannot propagate, the gradient doesn't propagate very deeply into a multi-layer architectures. So in the 80s, it was applied to network with 3 layers, one hidden layer. It worked nicely there, and that's what you could do with the computers at the time. But as soon as you went to deeper architecture, it was impossible to use gradient descent. Yes?
So I'm a little illuminating over this comment by Minsky and Papert. So I don't know this field. It's first a strange way of saying that there is no reason to believe X, which is not equivalent to saying there is reason not to believe X. And so what I'm curious about is, has anybody responded to their challenge in the sense of showing that without back propagation, these virtues don't convey to the multi-layer, and it requires back propagation to make, progress in this field?
I actually don't think that you require backpropagation. There is other ways to do it. So, and I'll show some of them later in the talk. So, I don't know of any such response. The other thing that the PDB group introduced, which is going to play an important role, is the idea of an autoencoder. So, an autoencoder is a very simple circuit where you have an input layer of size n, you have a hidden layer of size p, the output layer of size n, and the goal is to adjust the parameters of this transfer function so that the output looks as close as possible to the input. For instance, for L2 square norm or Hamming distance, that depends on the problem, but that's the basic idea of an autoencoder. Now, when you look at this, it looks completely stupid because you're building a circuit and you're trying to produce in the output what you already have in the input. You have your data. Why would you try to produce a corrupted version of the data in the output, right? But the beauty, the reason why this is such an interesting and deep idea, after all, is that you're not interested in the output. You're interested in what happens here in the hidden layer. And if the hidden layer is smaller, like in this case, it's sort of a bottleneck, you're forced to compress the data. And we know that compressing the data means understanding the data. If you want good compression, it means you have to understand the data. You have to find the right features, the most important component, whatever the exact mathematics of the problem is. But that's what this circuit is doing. And it's another way of addressing Hebb's problem. How do you learn things without being told what to do? Here I just use my data. I have data, it's completely unsupervised learning, but I'm learning to build somehow some kind of model or representation of the data in the hidden layer. In the 90s, it was all about graphical models, Bayesian networks, etc. Towards the end of the 90s, people started getting interested in kernel methods, SVM, etc. And so neural networks sort of disappeared for 10 or 15 years. And there was a sort of backlash against neural network, especially because in the 80s, some people claimed they were good models of the brain, right? And that, of course, we know that a single artificial neuron is very far from being close to biological neurons. So there was this backlash. It was almost impossible to publish a paper at NIPS if you had neural network in the title. And you had to say artificial neural network. If you didn't put the word artificial, you were really considered a bad person. And I think, and it's becoming, I think, more and more clear that this backlash was a sound thing at the time, but the pendulum swung a little bit too far. And the analogy I like to make is to say that neural networks have nothing to do with the brain. It's like saying Turing machines have nothing to do with cell phones. It is true at some levels they don't have GPS, they don't have Facebook, etc. But at some other level, they are fundamental for understanding processing in cell phones or computers. And I think it's a little bit the same thing for neural networks. So around 2006, this paper from Hinton, his group, and other papers came out, which restarted an interest in neural networks and deep architectures. And the paper was built using restricted Boltzmann machines, which are a particular type of random Markov field that I don't need to describe to you. I'm going to describe the same idea using neural networks because it's exactly the same thing. And this is the idea. So you want to build a deep architecture for some problem, let's say image recognition. You want to detect whether there is an elephant or not in a given image. And what you do, you take tons of images, anything you want from Google, for instance, and you train a first autoencoder that learns how to compress the data without knowing anything about elephants in this representation. You do it again. For each input, you get a value, an activation here after training. You take this as your new training set for the next autoencoder, which compresses data a little bit more. And you do it a few times. So you stack autoencoders, you train the first, then you use the hidden layer of the first to train the second, etc. You stack these autoencoders on top of each other, and then you finally put your discrimination unit that decides what's the probability that there is an elephant in the image or not. And now you train this whole thing by backpropagation. And the claim is that, so you have a completely unsupervised training phase where you just use your input data to extract this, increasingly refined representation, let's say, and then a final discrimination pass where you train the entire architecture. And in 2006, this was shown to work very well on certain problems. And so it was very intriguing and restarted the interest that we have in this deep learning problem. So I'm going to spend, if you want to try to understand this a little bit more mathematically, the first thing you have to do is to understand autoencoders better. So let me say a few things about autoencoders, what we know about autoencoders today and what they're doing, and then I'll show you some other algorithms complementary to this one that can allow you to train deep architectures. So I'm going to take a general view of autoencoders, again, by playing on the type of functions and hardware that are used in this network. I think helps a lot to understand them mathematically. So I'm going to define autoencoder as being a circuit of this kind with you have functions A and B here that belong to certain classes, and I want to be flexible for now on the classes. And you have an overall distortion function in the output, delta. Again, I'll use L2 matrix and Hamming distance in specific case, but that's the general framework. And so if you do that, you'll see there is many types of autoencoders. There is linear autoencoders, nonlinear autoencoders. If you take linear autoencoders, you can do them over the complex numbers, real numbers, finite fields, etc. Every time you have a linear space. And in the nonlinear space, of course, you have very large numbers of different autoencoders. So we would like to study these different classes. And when you do that, you begin to see that there are general properties that are important for autoencoders that you should study every time you look at a particular class of autoencoders. The first one is group invariances, whether there are any invariances in the input that leave the problem unchanged. If you are using L2, any rotation translation of the data usually in the input will leave the problem invariant. There is also invariance in the hidden layer. If you are, for instance, in the linear case, if you're doing A times B, if you put CC minus 1 between A and B, the problem is unchanged. So you change coordinates in the hidden layer, it doesn't change the overall solution. You want to know if the problem is how complex it is it NP complete, etc. You would like to know something about the landscape of the distortion function, of the error function. Does it have local minima, etc. And also there is a natural algorithm that is suggested just by the shape of this circuit, which is, well, optimize A first, then B, then A, then B, and keep doing that and see what happens, right? So I'm going to give you examples of things that you can prove mathematically, starting with the most classical and simple case, which is the case where you're using squared Euclidean distance as your distortion measure, and everything is linear. So A and B are matrices. You probably know this is doing principal component analysis, but there is a little bit more to the story. So what you're doing, basically, you're trying to find a rank P approximation to the identity function. This is what this is doing. And you may think that this is a convex problem because everything is linear, this is L2 squared, so it should be convex, etc., except that matrices of rank P is not a convex set. It's actually very, very non-convex set. So this is not a convex optimization problem. However, if you fix A, it becomes convex in B and vice versa, and so that's how you get your equations for the critical points or for the solutions and how you solve the linear autoencoders. It turns out that it has a very interesting landscape that looks like this, where the global optimum is principal component analysis or singular value decomposition, whichever way you want to look at it, where in the hidden layer you are basically projecting the data on the subspace that is spanned by the eigenvector associated with the top P eigenvalues. And then you have lots of other critical points where the gradient is 0, which corresponds to projection onto subspaces spanned by eigenvectors associated with eigenvalues that are not the top P eigenvalues. So very interesting landscape with a lot of saddle points and one global optimum up to these symmetries that you have in the space that is multiplication of by CC minus 1 here, changing coordinates in the hidden layer. So the real case is, I would say, completely understood. And if you look at the complex case, it's exactly the same thing. The algebra goes through. You just have to change transposition into conjugate transposition. And you also understand what happens when you do stacking, because if you do stacking like this, if I train, I'm going to extract the first P1 principal components of the data, and then in the second stage, I extract the top P principal component from that. So projection onto projections is well understood, and so you can understand what happens in the linear case, real linear case. When you do stacking, you're just compressing the space onto smaller and smaller subspaces spanned by optimal eigenvectors. If you are a mathematician, you may care about finite fields. It's not important for machine learning. So finite field, for instance, GF2, is the field where everything is like normal numbers, but 1 + 1 = 0. So very good for accounting. Goldman Sachs likes GF2 to do accounting on GF2. But anyway, the problem turns out to be extremely complex. It's very difficult to do linear autoencoders over finite field. You can show that it's NP complete. And even optimizing one layer, it's not clear how that can be done on finite fields. So it's a completely different story.
What was different about the dimensionality reduction in the second layer that caused you to reduce to a smaller number of principal components in that case?
You mean here when you stack them?
Yeah.
You're training first autoencoder, so it's projecting on a subspace of P optimal eigenvectors. You're training this data now, and you are projecting onto further smaller subspace. So if you go from 100 to 50 to 10, at the end of the day, it's like if you had projected.
I understand that, but I would have had some principal criterion for stopping at 50 in the first layer, and I would have thought that same criterion would have had me stay at 50 in the second layer.
That's a different issue. I'm not saying that you should do 100, 50, 10. I'm not recommending that. When you should stop and etc., that's a different set of questions. But if you were to do it, that's what it would do. But of course, in machine learning and other areas, you're interested in nonlinear autoencoders. And so the question is, can we solve a nonlinear autoencoder in a precise, more mathematical ways? And up to recently, there was no such solution until we started looking at the case of Boolean autoencoders, which are the most extreme form of autoencoder, of nonlinear autoencoder, where you imagine that you can have any Boolean function between, so your input is binary, your vectors are 0 and 1s, your arrow function is the Hamming distance, and between these two layers you can put any Boolean function you want. And same thing here. So you're completely free, you are unlimited power in terms of the Boolean function you're using. You're not limited to threshold gates or AND gates, anything like that. You can use any Boolean function. But you still have to address this problem of optimal compression if you want. So I'm going to show you that this system is doing clustering in some precise sense that you will see in a second. So the best way to show you that is let's try to understand what happens if you fix B, you try to optimize A, and vice versa. And let's start with the easy part, which is we fix the deep layer. We fix B. Let's try to optimize A, right? So that means that I give you a hidden vector here, and you have to tell me what should be the output. That's what it means to determine A, and it can be any Boolean function. So we need to find the target of this vector. To do that, I look at the predecessors. I look at the binary vectors in the input that are mapped onto this vector from the function B. Yes?
For those of us that don't know, is there a simple description of the class of Boolean functions?
Any function from binary to binary is a Boolean function, right? Nothing else. So I look at all the predecessors, all the vectors in the input space that are mapped onto H, and now you have to think what should be the output. Once you map all these vectors onto this vector, the information about these vectors is lost, right? That's what the bottleneck does. So you have to produce a single vector here that is the closest to these three in Hamming distance. So you can think of it as the Hamming center of gravity of these three vectors. It turns out it's the majority. You can show that it's the majority. So it's the vector that has a 1 in the first component, a 0 in the second component, etc. Of course, if you have an even number of vectors, etc., you can have tie, you flip a coin, it doesn't matter. But basically, it's the majority vector. So the majority vector, the majority of all the vectors in the input space that are mapped onto a single vector in the hidden space, that is the right output you should use for A. And you can see that you can study generalization in a very interesting way, because you can take the majority either on all the vectors that are mapped here by B, or on the subset of vectors in the training set. The training set is a smaller set than, and so depending how you do it, you're going to get generalization effect, and you can study them in this system. So it's very interesting for that. If instead of doing mapping the data to itself, you add targets, everything I said remains the same, because it would mean you have a target y for this vector, and for this vector, and so you now take the majority of the targets, the vector that is closest to the three targets. So this is general, can be applied to any Boolean circuit, not just the autoencoder circuit. Now let's look at the other way around. Suppose I fix A. So I fix the transformation A. It means that for every hidden vector here, I get an output. And I can look at the tessellation, if you want, of the Boolean hypercube that is created by this output. That is, I look at all the binary vectors that are closest to this output for the Hamming distance, and all the ones that are closest to this output for the Hamming distance, etc. So you get a partitioning of the hypercube created by the images of these vectors. And now if you take an input, let's say an input which is going to be inside this sphere, what should be its image in the hidden layer? It's obviously A of H1. It's going to be H1, right? That's the natural thing to do. So the entire Voronoi space, or the entire cell that is around one center, should be mapped to that center in the hidden layer. And this is why the system is doing clustering. It's grouping all the vectors that are sent to the same activity level in the hidden layer form a cluster of points, and then they are mapped to the center of gravity of that cluster. So you can understand in detail what happens, what the Boolean autoencoder is trying to do, and you can try this alternate optimization problem and see how well it does. And on real data, it does quite well. But you can show that the problem is NP-complete. The optimization problem in the Boolean case is NP-complete. And just to give you a sense of how to do that, you have to, of course, do this reduction between NP-complete problem. We know that clustering M point on a planar lattice, if you have M points on a 2D lattice and you want to cluster into K clusters, for the Manhattan distance, the L1 distance on the lattice, that problem is NP-complete as soon as the number of clusters is large, scales with the data. And so the question is, can we use that to prove that clustering on the hypercube is NP-complete? And the answer is yes, by this following mapping. You take your problem, so you have a clustering problem in the 2D lattice, and you map the 2D lattice to the hypercube by assigning one component on the hypercube to each vertical direction on the lattice, and one component for each horizontal. So when I'm moving from this point to here, I'm changing the first 4 bits. Each step is one of the 4 bits. And then when you move vertically, you're changing one of the 3 bits. And you can see that the L1 distance in the lattice goes exactly onto the Hamming distance on the hypercube through this transformation. So when you apply this transformation, if you could do the clustering on the hypercube, you would be able to solve the clustering problem for the Manhattan distance on the 2D lattice, and so the problem is NP-complete by this reduction. Okay, so let me now shift gears. That's all I'll say about autoencoders. Let me show you another possible algorithm for training deep architectures, which is not back-propagations, to answer the question that was asked in the audience. Pick a deep architecture, pick some input-output targets. The question is, how do you set the weights in these layers? One way to look at it is can you get targets for the weights in this layer? Can you tell this layer what the activity here should be, what is the right thing to do? Because if you give me targets, you have all kinds of algorithms, shallow learning algorithms, to fix the weights between two layers. For instance, gradient descent, right? Or SVM type of optimization algorithms. So we know how to do shallow learning. Perceptron algorithm is another shallow learning algorithm. The question is, we need targets. So the question is how to give targets to deep layers. So I'm going to show you one way to do it. So you take your input and you propagate it forward to this layer. And now the question is, what should it do here in order to do well on the function? Well, we don't know. What we're going to do is sample. We're going to sample in this layer, create a lot of samples. And there are issues, how do you do these samples? Maybe you should do them around the image of these vectors. But let's for now think you're going to produce a lot of samples in this layer. We're going to propagate them forward in the upper layer. So you get a sample in the upper layers. And now here we know what is the best of this sample, because we have the targets. So we choose the best and look where it came from here. What was the best sample here that produced the best sample here, and use this as the target for adjusting these weights. So that's what we call the deep targets algorithm, which is another way that doesn't require propagation of gradients. This requires only forward propagations and keeping track of which sample in this layer gives a sample in that layer. This is an example of a training experiment where we use threshold gates, which, by the way, if you have threshold gates, they're not differentiable, so you cannot do gradient descent, strictly speaking. But with this algorithm, you can do it. So this is an autoencoder 130, 10, 30, 100 that was trained using this deep target algorithm. You can see the error, both the training and the generalization error are going down and stay together in a nice way. This is an example of a 14-layer network, so quite deep network trained on the standard NIST data set. This is character recognition data set. You can see that gradient descent cannot do anything when you have 14 layers. The arrows stay flat, and this learns quite nicely. And we've done a fair number of experiments. This is another one. So the deep targets algorithm is another possible approach for training deep architectures without doing any gradient descent. Let me show you another set of ideas that are being used today for training deep architectures. I showed you the trick by Hinton of stacking these autoencoders. And one question you may have is, when you stack these autoencoders, they have no idea of the final task. They don't know if you want to recognize elephants or zebras, or maybe something completely different, right? So how do you know that the representation you're creating in these even layers is well suited to the task, right? So one thing you can do is to do a different type of training where you train this layer directly to discriminate elephants. So I'm training this to discriminate elephants. It doesn't do very well, but I add a new layer and then I do it again, and I do it again. That's another approach where you do discriminative training at each level. And of course, there is many variants, but I'm going to go directly to the last one, which combines all these ideas. So what you can do is you take your images and you train an even layer to reproduce in the output two things: the image itself, but at the same time, whenever you have a label on the image, whenever you know if there is an elephant or not, you have to predict this bit, 0 or 1. So the hidden layer has to learn these two tasks at the same time. It's what's called transfer learning, right? And so the fact that you're putting this additional bit in this layer forces the representation in the hidden layer to be a little bit tuned to the task you're interested in, which in this case would be elephant recognition. And you can imagine making, so you have an arrow function here that has two terms. It has a reconstruction term plus a discrimination term, and you can of course put a weight there, so that in the lower layer the discrimination has a small weight, and as you go up in the hierarchy, you crank up the weight so that the top layers have a very strong discrimination signal that influence the learning process. So this is just to give you a sense of all kinds of new ideas, fairly empirical, I admit that certainly, that are being used today to train these deep architectures in all kinds of tasks, combining unsupervised learning with supervised learning and in different ways, and using a multitasks approach. Let me show you one last interesting algorithm that was introduced again by Hinton's group a few months ago. It's called Dropout. You take a neural network during training, And then with probability 0.5, you delete neurons in the network. And you take an example, you train the corresponding weights, and then you do it again. With probability 0.5, you delete another sets of neurons randomly, and you train the weights. And you transfer the weights at each epoch. You do weight sharing. The weights are transferred from one case to the other. And you keep doing that until it stabilizes. And then at prediction time, the claim is you divide all the weights by 2 if the probability was 0.5, otherwise you have to adjust this factor. And the claim is that it works very well. People have tried this on data, and it does work quite well. It's not a universal solution, but it has some very interesting properties. And so the question is, what is the system doing, and why does it work well? Well, to try to understand this, so the basic idea is that what the system is doing is using an ensemble for prediction. And we know from statistics and other things that using ensembles, training many models is a good idea in general to have robust prediction. So this is a cheap way of training all the possible subnetworks of your network. Imagine you have the ensemble of all possible subnetwork, which is extremely large. And what this system is doing is picking one at random, training it, and then picking another one at random. So it's doing online training, stochastic gradient descent on the ensemble of all possible networks. Now, why is this true or even plausible? Let me try to show you that in a more mathematical way. And what happens if you use different values of P? What if you apply dropouts to connections rather than units? You delete connections rather than deleting neurons if you want. Why is it convergence, etc.? Very briefly, the first thing you want to see is to look at the linear case. So you imagine you have a pure linear network. So you have something like this, and the dropout here is represented by the selector function here, which is selecting neuron J in layer L. And if you compute the expectation of this output, you can see that all these terms being independent, the expectation of the product is the product of the expectations, and that indeed you get the expectation of this selector variable, which if you're using 0.5 is going to be 0.5. If you're using 0.6 for deleting neurons, you're going to get 0.6 here, right? So in the linear case, you can see exactly what is going on. Is that you're computing this expectation, this average over all possible network is indeed computed by this expectation. But why should anything like this be true in the nonlinear case where you're using sigmoidal things? So I'm using sigmoidal functions. Here's a function that computes a linear sum S, pass it through the sigmoid to produce the output. If you look at all possible subnetwork of this function, that is all the possible subnetwork that are computing this S, you can take not the expectation, not the normal average, but you take the geometric mean, if you want, of these different networks. So here is the different networks with some probability P, which can be produced by this Bernoulli selector variable, for instance, but it could be another distribution P. And this is the geometric average, the product of all the outputs weighted by the probability of the corresponding network, right? Now, this formula is a little bit more complicated. It's called the normalized geometric average, because you have the geometric average, but you have to normalize by this and the prediction, if you want, of the opposite class here. Again, taken over all possible networks. So that's the normalized geometric average. And the theorem that you can prove is that the normalized weighted geometric average over all possible networks is exactly the same thing as taking the sigmoid and applying it to the expectation of the sum, which is linear, right? So that's an exact inequality. Furthermore, if you take Taylor expansion, you can show that this is an approximation to the expected value of the output of all the networks, which is really the quantity you're interested in. You're taking the expectation of all possible networks. That's the ensemble average. It's very well approximated by applying the sigmoid to the average activity, average linear activity of the corresponding unit. And so these are the equations that allow you to propagate the expectations from layer to layer with this approximation, and to show that, yes, indeed, these networks, when you divide the weights by 2 if p equals 0.5, are computing something very close to this, which is the expectation over all possible subnetworks contained in the network. Let me finish by giving you an example of an application. So in the past year, these deep architectures of one kind or the other have been able to improve all kinds of benchmark data sets in image recognition at Google, for instance, in speech recognition, natural language processing, you name it. All the latest benchmarks on large data sets have been improved by several percentage points by these deep architectures. And one contribution, one data set on which we worked is in protein structure prediction. And just to give you a flavor of the type of architecture we use there is that every time you have an acyclic graph, like a Bayesian network, for instance, you can always convert this to a deep neural network by replacing the conditional probability distribution between the nodes by a neural network. And if your graph has some kind of regular structure, you can do weight sharing and use the same network in different places. So for protein structure prediction is a well-known, very difficult problem which has many facets. You can predict secondary structure, the position of alpha helices along the protein sequence, or the position of beta sheets or beta strands, these arrows that you see here, coils. That's called secondary structure prediction. You can try to predict 3D structure, which is the XYZ coordinates of the atoms in this structure. You can do it for the backbone, the C alpha, C beta of the protein, or you can do an all atom calculation if you want the side chains. There is quaternary structure when you have proteins interacting with each other and forming protein complexes, and you want to have the 3D coordinates of all the chains in the complex. So there is all kinds of sub-problems within protein structure. But this is the kind of architecture you can build, for instance, for secondary structure prediction. So here is your protein structure. You take a window, and this is sort of a Bayesian view, Bayesian network view of your prediction system, where your prediction at position t, which should be the probability of alpha helix, beta strand, or coil, is a function of the input window, what's in the input window, and then on the hidden values that are on the backward chain and the forward Markov chain of this Bayesian network. And again, you can take this and transform into a deep neural network architecture by using essentially only 3 neural networks. One that computes the output probabilities as a function of the vector b, the vector f, and the vector u. One that computes the vector b at time t as a function of the vector ut and the vector bt plus 1. And one that computes the vector ft at times t as a function of ut and ft minus 1. And you can, in order to keep the number of parameters small, you of course assume that the network here is the same as the network here, etc. That is, you do weight sharing in this forward chain, and weight sharing in the backward chain, and weight sharing in the output chain. So this is called the recursive neural network architectures. It has been used for secondary structure. I won't go into the details, and does very well. There is a predictor called SSPro that you can use to predict secondary structure using that. But of course, the difficult problem is how do you go through 3D structure, right? And you have to think about this problem because the structure of the protein is invariant to rotation and translations. And so how do you deal with that when you have neural networks? And one idea is to use a representation that doesn't depend on translations and rotation. And the one we use is the contact map. So the contact map is a matrix, symmetric matrix, very sparse, of 0 and 1s. You put a 1 here if the I and j elements are close to each other in 3D. So if you do it at the level of amino acids, I and j are amino acids in the sequence, are letters in the sequence. The protein folds. If they end up at less than 8 angstrom away in the folded structure, you put a 1 in the matrix, otherwise you put a 0, right? There are subtleties. You can do contact maps at different thresholds, etc., but I won't go into the details, but that's the contact map. And so the idea is how you can predict a contact map, And what is, of course, most challenging and most interesting is to predict this corner. That is the long-range residues of the protein. The ones on the diagonal or close to the diagonal, we know how to predict. But if you can predict this corner here, that's really, you would have solved the protein structure prediction problem. So we use a recursive architecture, fairly similar, I mean, same ideas as what I've shown you before for the secondary structure. These are just examples of contact maps so that you see how they look like in case you've never seen a contact map. This is the recursive approach we take. I don't have time to go into details, but to make a long story short, at the last CASP experiment, this is an experiment that takes place every 2 years, where people do blind prediction on proteins that were solved by crystallographic methods, NMR methods in the last few months. And there is different categories. This is the contact map prediction, residue, contact prediction. The first two methods that got the best scores are both deep architectures. So that's another example of a recent success. And we have built a suite of programs for predicting different properties of protein structures and 3D structures. They are all available on the internet. You can download them. You can submit a protein and get your prediction backs via email. These are some references that you can find on my website. And to finish, there are many, many students and postdocs that I should thank and I could thank, but rather than do that, I want to leave you with this picture, which is really the topic of my of this talk, which I think is the most interesting thing I can leave you with, and it's the idea that deep learning is at the center of this triangle, where on one hand you have evolution, which has used learning over billions of years to understand how to take advantage of carbon-based computing and to build genomes that are capable through development, interaction with the world, to build extremely sophisticated carbon-based computing system like the brain, which of course uses deep learning for all kinds of things, from perception all the way to skills like mathematics, learning how to do complex mathematics. This brain has been able, through deep learning, to develop silicon-based computing systems, computers, where we're now trying to implement deep learning into these systems and using that for analyzing data, including genomic data and protein data, and closing this loop in this very strange way. And if you think that genomes have nothing to do with learning in the brain, you better look at that more carefully, because we're finding more and more that the genome plays an essential role in memory. If you run a mice through a maze and you look at the level of expression of the genes, for instance, in the hippocampus, after the experiments, and you compare it with the level of expression in a mice that has not been run in the maze, or a mice that, or in other parts of the brain, we know by now that there is all kinds of proteins that are very specific to learning that are activated during learning experiments, proteins that probably travel all the way to the synapses, and by doing so, modify those synapses ultimately so that you can implement your memories and store your telephone number or other things. In addition, there are chemical modifications that are applied to the DNA double helix itself, which are called epigenetic modifications, throughout the life of a neuron, for instance, during differentiation. And these chemical modifications are fairly stable and are also a form of memory. And it's not clear how far this analogy goes. It could be, it is not impossible, that when you're storing your telephone, ultimately, there are chemical modifications that are very important for that storage that are happening at the level of the DNA. So thank you for your attention, and I'll try to answer any questions.
So we have time for a few questions.
You had to go through it fairly quickly, but I'm curious for your protein structure predictions. How large a network of neurons were you using, and how does that map onto the physical structure?
So let's talk about contact maps, which is close to So if you're trying to predict contact map, the first thing you have to realize is that you are in a situation where you're trying to predict outputs that have different size. Right? If a protein has 100 amino acids, it's going to be 100 by 100. If it has 400 amino acids, it's 400 by 400. So it's variable size input and outputs. So it's very different in that sense from the case where you have vectors of fixed length or image processing where all your images are the same size. So your system needs to be flexible and adapt to variable structure. Right? That's the first thing. So these recursive networks are very good for that problem. So the one we use for contact map prediction, you have an input plane, which is the size of the protein. So if the protein is 100, this is going to be 100 by 100. You're going to have 4 hidden planes, 4 hidden lattices, and one output at each position. The output is the probability whether there is contact or not between I and j. And this probability is going to be a function of 5 vectors, your input vector. So what is the input vector is going to be a window around I, a window of I around j with all kinds of information. You know, the type of amino acid, their size, hydrophobicity, whatever. These are 4 hidden vectors in the 4 hidden lattices that are propagating contacts laterally in different directions. So you want, when you predict contact map at position ij, you want to know something about the protein in regions that are further away than the input window. So that's what the 4 hidden states are supposed to be. When you convert this Bayesian network, or the graph is acyclic, into a neural networks, you're going to end up with 5 neural networks, one that computes the output, and 4 neural networks for the lateral propagations. So your question is how many parameters the model has, right? It depends on how you structure these 5 networks. So each one of these 5 networks typically has one hidden layer and one input layer. So we end up with models that have from 10,000 to 100,000 parameters, to give you a sort of ballpark number. People are doing image recognition today with 1 billion parameters at Google. So the range, the size of the model has definitely gone up due to data availability and computer power, the combination.
What do you train this one on? Do you train it just on all available structure data?
Well, we do cross-validation. So we train on, say, 2,000 protein structures from the PDB, sort of 2,000, 4,000, and then we have holdout data sets, so we use CASP data to do the testing. And it's still very far. I mean, we got the best result at the CASP experiment, but it's still very far from being very accurate. So the problem is far from solved. How to predict the 3D structure of a protein is not a solved problem by any stretch of the imagination. Yes. Yes.
So, is it true that as I increase the number of layers in the deep architecture, I see consistently improving performance, because that's what the NNIST data set seems to indicate?
It is not true in general.
So
usually you will see some increase at the beginning, and then it will plateau or even start deteriorating. So it's not true that the more layers you have, the better. We also know that everything can be done in a single layer, but it may be of exponential size, right? So
do we have a prescription for how many layers is good?
No. There is no theory of how many layers is good, as far as I know. It's all empirical and trying different numbers of layers. There are a few Boolean circuit, results that show that certain function requires, the scaling of the number of layers has to be at least that many, etc. So there are a few isolated results in circuit complexity, but they are not practical.
Intuitively, there seems to be 2 forces, right? In the deep targets algorithm, the deeper the architecture, the more error you accumulate as you propagate things forward. I mean, you need a larger and larger sample to get the target matching, but also having a deeper layer allows you to model more complex things with fewer, thinner layers. So,
Yeah, sure.
Any other questions? Okay, well, let's thank our speaker, and there are refreshments next to that.